Alright, welcome everyone that's here and watching the recording to our second day of duality, duality theory. First, a few announcements. Homework 4 is due tonight, I believe. And I will post the next homework sometime today. Office hours today have been moved forward an hour. So they're 3 o'clock to 5 o'clock. I may be able to spill over a little ways, but I've got I've got something coming up this evening, so might be difficult for me. So 3 to 5 I'll be available to talk about homework 4 or anything else. I've graded homework 3, and a lot of people were struggling with it. The different coding methods, and I'm thinking about adding in an optional extra homework assignment that would be more practice with software implementation that could overwrite your homework 3 grade if you're not satisfied with it. I'm thinking about that. The problem is we already have so much else to do, so we'll. But if that sounds good to you, let me know, and I'll take that into consideration. I think that's everything I wanted to say announcement-wise. So let's jump into the content. Alright, duality part 2. So yesterday we came up with the dual problem for an LP, and we talked about how to form the dual and how to make sure that the dual was a bound on the optimal value of our primal problem. So today I want to codify that result a little bit more. What we talked about yesterday was weak duality, or the result we had yesterday was weak duality. We'll make that theorem a little more rigorous, a little more codified, and then we'll talk about strong duality, which is a slightly different statement based on the dual. And then we'll talk about complementary slackness. And maybe to the chagrin of some of you, we're going to do a rigorous mathematical proof for strong duality. I'm a mathematician by training, and I really enjoy rigorous proving. And finally, I have an excuse where the proof is actually important. It's actually important to understanding how it works and how strong duality leads into the next section, and in fact into sensitivity analysis, which is what we'll do on next Tuesday, I believe. So I have paper notes this time. I have a proof written down here. It's similar enough to the proof that's in the book, but it's my own sort of take on it that I think highlights some of the important aspects a little better. I'm looking forward to this. I always enjoy proofs. and I would say you guys are lucky to not that I've shown restraint and not proven every little thing we've done so far. So let's get into this. I'm excited. I like this stuff. Okay, so what we did yesterday is we came up with the dual problem, the dual of an LP. We called it the primal LP. Today we're going to call it P, and the dual is D. Yeah. So again, I've gone back to my bad habit of kind of flubbing the domain constraints for this particular aspect, just because it's not sort of the important part of the theorem. The important part is the constraints and the objective functions. When you are, if you are actually using the dual, the domain constraints are vital. They are maybe the most important part of the dual. Um, so keep that in mind when you're actually forming the dual in the homework we will have on duality and sensitivity analysis. So we showed yesterday that if we have a primal dual pair and feasible solutions, x and y star, for the primal and the dual, then we always knew that the primal objective function value was less than the dual objective function value. And here we're assuming that the primal is a maximization problem and the dual is a minimization problem. It's simple enough to remember that the dual of the dual is the primal, and to flip this result around if you have a minimization primal, and that would give you a maximization dual. Further, we recognized that if we had two feasible solutions for the primal and the dual that had equivalent objective function values, then both of those solutions were in fact optimal to their respective problems. That is weak duality. That's the formal theorem of weak duality. Now there are a couple of corollaries to weak duality. A corollary, if you haven't heard the term before, is just an additional result that follows from a theorem or a lemma or a statement or whatever you have. It's an additional result that is relatively easy to prove and doesn't require pages and pages to demonstrate formally. So our corollary is that if P is unbounded, then D is infeasible. So if P is unbounded, if the primal problem is unbounded, then the dual is infeasible. Similarly, if the dual is unbounded, then the primal is infeasible. And the third is that if both the primal and dual are feasible, then they both have finite optimal solutions. Finite optimal solutions. We're going to demonstrate this by considering what's called the contrapositive. The contrapositive just means that we negate, if we have an if-then statement, if-then, like our first two here, we can negate both sides of that if-then and then swap them. And the contrapositive is in fact logically equivalent to the original statement. So if we can prove the contrapositive, that is sufficient to prove the original statement. That's a technical mathematical uh, thing that if you took, if you endeavor to take Intro to Mathematical Proof, which I don't know what that is at this school, what number that is, but it's in the math department. I really recommend that class. I love that stuff. You'll learn more about contrapositive and how it's used, but I'm just going to use it here because I think the contrapositive is a little more, it's a little easier to show and gives us a little more insight, I think. In fact, the book proves the contrapositive, but it doesn't call out the method it's using. So the contrapositive of the first two statements of our corollary, really, the third statement is in fact has not been changed at all. So the first statement, it was, if P is unbounded, then D is infeasible. We negate both statements and then swap their if-then ordering, and we get, if D is not infeasible, then P is not unbounded. So this is the same logical statement that we made in the previous slide, but I think it's a little easier to show. So let me come back here and say if, well, so if D is not infeasible, i.e. There exists a feasible solution to D, to the dual, then we have some solution Y for the dual that, by the construction of the dual, has to upper bound the primal, which means that the primal objective function value can only get as big as B transpose Y. Is bounded by B transpose Y for any dual feasible Y. So since there does exist a dual feasible solution Y, the primal is bounded. We use exactly the same logic on statement 2. Let me just copy this. The dual objective value is bounded by C transpose X for any primal feasible X. So if there is a primal feasible X, we have C transpose X, which acts as a lower bound on the dual, on the minimization problem. So that is very nearly a formal proof of that, those two statements. So let's think about the final statement. If P and D are both feasible, then they both have optimal solutions. So if something is not infeasible, then it is instead feasible. And so if P is feasible, which we are assuming for this statement, and then uh, since P is feasible, D is not unbounded, and we have the same result if we just erase these. Since D is feasible, P is not unbounded, which means that so both P and D are feasible and bounded. The only other option is that P and D have finite optimal solutions. So that's a corollary, just because we proved it relatively easily. It didn't take much to prove. But there's still important results. We already knew that the primal and the dual had sort of an uncanny relationship. They bound each other, they have the same optimal solutions. But it's neat that if we can show that one is unbounded, then the other is infeasible. It's useful sometimes for showing infeasibility, which is a boon. So here's the full statement. Here's the proper theorem, and here's the corollary that we just showed. Yeah. And remember that if we swap this for a minimization and this for a maximization, the only thing that changes is the direction of this inequality. So there's weak duality, formally. So now we need strong duality. So we're going to let P and D be a primal dual pair of linear programs. If either P or D has an optimal solution, then the other of P or D has an optimal solution. Now this sounds like this sounds very similar to weak duality. So let me back up and we can point out the differences. So here we said we had that if given feasible solutions to both problems, so for weak duality to apply, we need to have feasible solutions to both problems. We need to have found feasible solutions already. Then we have this relationship. And if this holds, then those solutions are optimal. In strong duality, if we have an optimal solution to either problem, we know that there exists an optimal solution to its dual. And in fact, we'll see in the proof that we can express well, we'll need complementary slackness to fully show it, but we can actually express the optimal dual solution in terms of the optimal basis for the primal problem. So, what I'm going to do now is formally prove the strong duality theorem. And it's a little bit technical. We're going to do some matrix algebra that is a little bit confusing, but I don't think it's too hard. I think it's actually rather elegant on the whole as proofs go. I really enjoy it. So maybe some of you will get some similar satisfaction from seeing this proof. If you don't worry about it. That's not a big deal. You can like what you like, but I like this stuff, so we're going to do it. So, the first thing we're going to do is let P be a linear program in standard equality form. And remember that we can put any linear program in standard equality form. So this is not actually restrictive to the theorem or the proof. This is without loss of generality. Any LP can be expressed in SEF, standard equality form. And define D to be the dual of P. So let's write those explicitly. P is maximize C transpose X such that AX equals B and X is greater than or equal to 0. And the dual of that is a minimization of B transpose Y such that A transpose Y is greater than or equal to C. Since we have a maximization with greater than or equal to or non-negative variables, we have a greater than or equal to constraint. And that's it. That's the whole dual. The Y variables happen to be free. So yeah, that's our dual. Then we know a few things from the statement of the theorem. We're going to assume that P is the one that has an optimal solution. So suppose there exists an optimal solution x star to the primal problem with or corresponding to the basis, or the optimal basis B. I'm going to call our basis B. Let's write P in the canonical form for this basis. And consider the canonical form of P for basis B. Remember, B is our optimal basis. So we go back to our equations for the canonical form. I'm going to call this P prime, and we're going to it's still a maximization problem. And we have C transpose B A inverse B lowercase b C transpose minus CB transpose AB inverse AX. Such that AB inverse AX equals AB inverse B, and X is non-negative. So I'm going to grab this. I didn't do it. Grab that, paste it on our next page so we can reference it, and move along. So this is stuff we've seen before, right? We've seen the canonical form. We mostly deal with it in the tableau, but we justified those equations in one of the lectures. I forget exactly what it was titled or what number it was. So we have our canonical form for the optimal basis. And we're going to suppose that we found this optimal basis from the simplex algorithm. Or that we're going to assume that the simplex algorithm told us that this basis was optimal. And so remember then, when does the simplex algorithm tell us to stop? So the simplex algorithm terminates at an optimal solution when this term is less than or equal to 0, or more specifically, the 0 vector. So that term is the term in our tableau that goes in our variable columns. And typically in the tableau we negate that that column, and for maximization we would look for negative values, and we would terminate when we had positive values. Since we negated that, we actually here would terminate when we had no more positive values in that vector. So it terminates at an optimal solution when C transpose minus CB transpose AB inverse A is less than or equal to the 0 vector. I'm going to get rid of these parentheses and drag this to where I can work on it. Now we're going to do some algebra on this to get it in a form that we like a little better, or tells us something about the behavior of the dual. So this becomes so we subtract this term over, and then I just swap them around. Oh, that's not 0. That is C transpose. And then I'm going to transpose everything. So that we have C on the right side. We're going to distribute out that transpose somewhat. The inverse transpose, so let's AB inverse transpose is the same as AB transpose inverse, and we just write that as AB inverse transpose. And then we are going to notice that this term is actually a vector which is feasible to the dual problem. So let's go back and look at the dual. Its constraints were just A transpose Y greater than or equal to C for whatever vector Y that fits there. A AB inverse transpose times CB is a vector, and it has um, appropriate dimension for that multiplication to work. And so it is actually a feasible solution y equals, we're going to call it y star actually, y star equals AB inverse transpose CB is a feasible solution to the dual problem. And that's really neat, I think. That the primal, the optimal primal value in some way informs a feasible solution to the dual. And it only gets cooler from there. Because we're now going to think about the whole objective function I'm going to put p prime there. I'm going to grab this so we can reference all that without going back and forth. Now consider the objective function of p prime. We don't need this screen anymore. I'm just going to copy this. And remember that the objective function of the standard equality, or the canonical form, actually has the same value as the original problem. Excuse me, for the same solution. So we're going to put in our optimal solution for P, which was x star, and then do some more algebra. So this term can be rewritten as A inverse transpose, or A B inverse transpose CB times B. And then we can expand this out to non-basic and basic respectively. And I'm going to do the same operation, inverse transpose CB transpose A times the non-basic variables plus, or this should be A n. And I'm not going to do that same operation over here. CB transpose minus CB transpose AB inverse AB, XB, and these are both our optimal basic and non-basic variables, respectively. Or inverse, respectively. I said those backwards. So, this is y by our definition up here. So we're going to substitute that in, y transpose b plus cn minus y transpose an xn star, where this is star, plus CB transpose minus CB transpose AB times AB inverse is the identity matrix. Which, yeah, so we'll leave it like that. Xn is the non-basic variables for the optimal solution. And we're at the base, and the basis we've assumed is the optimal basis. So this is the solution that corresponds to the basis, which means that all of the non-basic variables are 0 for that solution. So we're at the basis we're in the canonical form for. The solution corresponds to that basis, which means that the non-basic variables in that solution are 0. Because that is, in fact, the definition of basic versus non-basic. This is just CB transpose times 1 minus 1 if you want to factor everything out, which is, of course, 0, the vector 0, which means that those second two terms cancel out, and we're left with CB, we're left with y star transpose b, which is, of course, a scalar, because we're doing a dot product. So I can transpose this and change nothing. So we get b transpose y star, which is the objective function for the dual. Value of y star in D. And we've already established that y star is feasible to the dual. And we're going to remember, in fact, we're just going to recall that x star is feasible to the primal. In fact, it was optimal to the primal, but all we need to know is that it is feasible to the primal. Therefore, or need one more statement here, is feasible to P, and thus to P prime. Because of course we worked with the objective function. Oh, well, actually, do we need that? Not necessarily. I'll leave it in for a little extra clarity. Therefore, we're getting behind my head here. Therefore, since y star is feasible to D, or to the dual of P, which is D. And C transpose X star equals B transpose Y star. Y star is optimal to the dual problem by weak duality. Where has my mouse disappeared to? Move this up a little bit to give us some more space so we can see it all better. And I'm going to space this out a little bit. Whoops. So this theorem is called strong duality because it's different from weak duality, but we use weak duality to prove strong duality. And it's not a corollary because it takes some effort to prove. It's not. It doesn't just follow sort of easily. It took us 3 pages to do. Yeah. So what can we pull? So this is the end of the proof, actually. Traditionally, one writes a small square at the end of your proof, which is now behind my head because I put it there. This just says, that just marks the end of the proof. If you followed all of that, excellent. If you found that satisfying, most excellent. If you didn't find it satisfying, oh well. I'm going to point out the important aspects going forward to this. That is from the proof, if x is optimal to the primal, and corresponds to the basis B, then y star equals AB inverse transpose CB is optimal to the dual. And of course we started with the primal in standard equality form. So we can we could take the contrapositive of this and use it as a certificate of duality or of optimality for the primal. This is just another way to verify optimality of the primal. In case anyone doubts, should there have been a C, B there? I don't think so. Yeah. So I just want to verify the dimension of y star, so that we're all convinced that it has the right size. If P had n variables and m constraints, then A was in n by m matrix, or correction, it was actually m by n. But the basis has the basic sort of thing. The basic matrix AB is a square matrix, and it has as many columns as it has rows. The rows were corresponding to the constraints. So it's square by the number of constraints. CB is actually also the same, because our basis is the same number, is the same size as our number of constraints. So we pick out M again, basic the M basic C entries, which means that so y star is in Rm by M times Rm, which is slightly sloppy. It's just saying we had a square times a thing, which gives us Rm, right? So it has M entries, and it has one entry for every constraint. That is, there is one y variable for every constraint in the primal problem. So y has the correct size, so we don't need to worry about that. So that is all really neat, really elegant, and important. It's especially important when we get to integer programming and nonlinear programming, because in certain cases these two theorems, weak and strong duality, still hold. Maybe not in quite the same form, maybe not in quite the same strength, but they still hold, and they still help us to determine how close we are to optimality, or how, or whether or not we are optimal at a given solution. So these are important theorems, and I felt it was good practice to prove one of them, especially because strong duality informs our next big topic, specifically the proof of strong duality. This idea that the optimal solution of one informs the optimal solution of its dual, of the other. That's very important. Let's see, how many extra pages did I have here? Okay. So is this the right page? Yeah. I'm going to come back here and grab our primal and dual problem again. I can't help but grab other things. So we have our primal and dual. And let's add slack variables to the dual. I don't want to put it fully in standard equality form, but I just want to add slack variables. D prime is the minimize, a minimization, B transpose Y, A transpose Y plus, or actually, this is minus, because we have a greater than or equal to. The slack variables equals C, where the slack are non-negative. So we added slack to the dual. And D prime is still dual to the primal. You can see that. You can convince yourself of that. The first step is to notice that the slack variables don't contribute to the objective function value. So they're not actually contributing to the bound that we're putting on the primal. So D prime is still dual. So now let's look at the objective function of D prime. D prime, is that what I want? Actually, we're going to look at the objective function of P. The objective function of the primal. C transpose X star. We're going back to our optimal solution, X star. And it, we can transpose that, right, because it's a scalar. And replace C with this. We have that equation. Since it's an equation, we can just drop that in without worrying about inequalities or swapping signs or anything. A transpose Y minus S. Replace our C with that term. And we get X star transpose A transpose Y star. Do I want Y star there? I think I do. Yeah. Plus X star transpose S. So X star times the slack of the dual. Then that further simplifies to AX star transpose. We're just going to transpose the first two terms here. Times Y star plus, again, X star transpose S, which then AX equals B from our primal problem. So let me demark that. B transpose Y star plus X star transpose S. So we've done some more goofy, convoluted matrix algebra, but we've seen something, or we found something important. I'm going to scoot all this up to give us more space. Remember that X star was optimal, and in fact Y star were optimal. And we saw that, we found that out by identifying that equation. But now we're saying that C transpose X equals B transpose Y plus something. Well, we already know that B transpose Y is equal to C transpose X. So X star transpose S must equal 0. X star transpose S equals 0. And remember that S is the slack for the dual problem. And this seems perhaps inconsequential, but it's actually, I would argue, the most important thing we've seen today. This term, this condition, is called the complementary slackness condition. And it's been proved that if we have a primal dual pair that adheres to the complementary slackness condition, or solutions that adhere to that complementary slackness condition for a linear program, that those two solutions are optimal. So this is yet another way to demonstrate optimality in a linear program, is to show that complementary slackness holds. you'd have to show it in both directions. So we need to get the slack from the primal and show that it matches the uh, the dual variables, that it's complementary to the dual variables. But you could use that to show optimality. Um, this uh, this complementary slackness generalizes slightly to what is called the Karish-Kuhn-Tucker conditions. Three guys, Karish, Kuhn, and Tucker, identified these conditions. I'm not going to go into detail about what exactly they are in this class. We will talk about them at some length in the fall in DOR2 because they are sufficient to prove optimality for nonlinear programs, which is an enormously important result for nonlinear optimization. So complementary slackness is a big deal, and I'm going to in the follow-up. I guess tomorrow is our question catch-up day. We're going to dive a little bit deeper into complementary slackness and be a little more thorough. Not much, just a little bit. A little more rigorous in explaining what that condition actually means. And then on Tuesday, I believe, we're talking about sensitivity analysis, which is again going to reference complementary slackness. So today was a heavy math day, heavy algebra. But we got to some very neat and very important results that maybe you will never use in your careers doing modeling, but are actually very fundamental to how solvers, especially nonlinear solvers, function, how they work. So that's all the content I have for today. I want to remind everyone again that my office hours today have been bumped forward an hour, so they are 3 to 5 instead of 4 to 6. I don't think I corrected it on the schedule on Canvas. Maybe I should do that. Hopefully, I will post the next homework, hopefully before office hours, but sometime today they will be posted. So I'll stick around for a little while, answer some questions, but you guys are free to go.